Okay, 12.2 combinations in the binomial theorem. So let's start with combinations here. Combination is an unordering of groupings, and the order does not matter. So we're just finding different combinations of things happening, but the order has no importance, and the grouping is not important either. Combination is almost identical to permutation, literally almost identical, and once again, we will go over it with how to use a calculator to solve that, but not right now. I want to make sure you understand first how to use it with factorials. Once we are done with that, then I will show you where it is in the calculator. If you're smart enough to figure it out on your own, then great. If not, I'm not going to show you how to do it yet until we get to the examples. But anyway, it's NCR. Permutation was NPR. This is NCR. Okay, so literally what we're saying here is this is the formula, almost identical to permutation, right? Permutation formula was n factorial over n minus r factorial. The only difference is with combination you have an r factorial there on the bottom again as well. That's the only difference. So combination is almost identical to permutation, except it has an extra r factorial there at the bottom. So if you have two objects taken from 5, once again, just like I told you with permutations, exactly like I told you with permutations, the larger number goes out in front. That's always your n. So see how it's 5c2? That larger number needs to go out in front. Okay, so you can't have 2c5. That wouldn't work, and it needs to be 5c2. So 5 is your n, so I plug in n on top, so it's n factorial. Then I subtract the 2 to get 5 minus 2 factorial, and then whatever your r is there. We end up with 5 factorial over 3 factorial, 2 factorial. And look at this, 3 factorial, 2 factorial. 3 plus 2 is 5. So they add up to 5 is the other point that I want you to keep in mind. So whenever you subtract them, whatever that answer is, the other one, they have to add up to give you the 5. So when I write that out, 5 the whole way down to 1, 3 down to 1, and 2 down to 1, I can cross out the 3 the whole way down to 1 on both. And if I wanted to, the 1's gone. I could divide that by 2. 4 divided by 2 is 2. So 5 times 2 is 10. So your answer for 5c2 is 10. So for example 1, a standard deck of 52 playing cards has 4 suits with 13 different cards in each suit as shown. If the order in which the cards are dealt is not important, how many different 5-card hands are possible? You have 52 total cards, right? 52 total cards in a deck. 5 cards are being drawn from it. So what's the total? 52 is the total, right? 52 is the total. You're choosing 5 cards. So when I go to plug this in, 52 is my n, so that's n factorial, over 52 minus 5 factorial, which is 47, and the 5 factorial is there at the end. And once again, notice that when you add those together, you get 52. How do I know I'm using combination? Did you ever play cards before? If you've ever played cards, you know that, yes, you might want to get pairs, and you might want to get 3 of a kinds and flushes, but it doesn't matter when you get the card, right? It doesn't matter. I could get a straight, but it comes in 8, jack, 10, queen, 9. It doesn't matter the order that it comes in as long as I get it. That's all that really matters. So the point I want you to keep in mind is that's how I know we're using combination, because we're talking about playing cards and it really doesn't matter the order that they come in. So I can take 52 factorial the whole way down, but as you know, that will probably cover up the entire page here. But what I can do is I'm going to show you a little trick. I took 52 the whole way down to 47 factorial. Why did I do that? Because I have a 47 factorial on the bottom. Since I have a 47 factorial on both the top and the bottom, that's why I did it. And this is the big reason. The big reason is these two are identical, because what is 47 factorial? That's 47 times 46 times 45. It can continue on anyway. So the point is, why write all that gibberish out if I can get it to stop? So 47's cross out, so all I have left is that on top, and 5 factorial is 5 the whole way down to 1. So I just can literally do 52 times 51 times 50 times 49 times 48, get an answer. and divide that by whatever the answer is at the bottom, which is 5 times 4 times 3 times 2 times 1, and you end up with 2,598,960 as your answer. In how many of these hands are all 5 cards the same suit? Well, we need to first choose an actual suit. There are 4 suits and you are choosing one. So before we sit down, I'm not going to sit there and say, oh, 52 cards, so I'm choosing 5 cards. No, when you're doing this, what's the likelihood of you choosing 5 cards of the same suit? Before I start choosing anything, okay, before you start doing anything like that, what you need to sit down is you need to think about, first I need to choose the suit. Well, how many suits are there? There's 4, and you're choosing one suit. Then, after that, how many cards are in each suit? There are 13 cards in each suit, and you're choosing 5 cards from there. So this right here stands for you picking a suit. This here stands for once you pick the suit, pick your 5 cards from the suit. So we're trying to think of all the different combinations of that happening. So that's saying this one is 4 factorial over 4 minus 1 factorial, 1 factorial. So that's 4 factorial, then I did 3 factorial, right? So I can get those to cross out. This is 13 factorial over 8 factorial, 5 factorial. Notice how I went the whole way down until I got to 8 factorial because that's on the bottom. So I can get the 3 factorials to cancel out. I can get the 8 factorials to cancel out. So really I have 4 on top times 13 times 12 times 11 times 10 times 9 over 1, because 1 factorial is 1, and 5 factorial is 5 times 4 times 3 times 2 times 1. I got the 4's to cancel out. 5 times 2 is 10. I still have a 3 in the bottom, which I can divide by that. 9 divided by 3 is 3. And really I have 13 times 12 times 11 times 3, which is 5,148. Example 3 here. A theater is staging a series of 12 different plays. You want to attend at least 3 plays. How many different combinations can you attend? Well, what I need you to keep in mind here is at least 3. At least 3 plays means you can go to 4 plays, 5 plays, 6 plays, 7 plays, 8 plays, 9, 10, 11, or all 12 plays. So, in other words, to solve this problem, it might be easier to think about it in reverse. And what that means is I would need to do the combination of every single one of those plays. From 12C3, me seeing 3 plays, 12C4, me seeing 4 of the plays, 12C5, me seeing 5 of them, the whole way on up. Or I can think about this in reverse. I can think about it of me only not seeing at least 3, but what about me seeing 2, 1, or 0 plays? So what I'm going to do is I found the total. I can either see the play or not see it, which is where that 2 comes from, and there's 12 different plays. So that's the total of combinations of me going. And I can choose to go see 0, 1, or 2 of those plays. So really what I'm doing is I'm finding the combination of 12, 0, of me not seeing any, 12, 1 of me seeing one of the plays, and 12, 2. And basically when I did that, plugged those in with the factorials, I got a 1, a 12, and a 66. And I subtracted them from the total, which was 4,096. And I got the total again because there were 2 different choices out of 12 different plays, and you end up with 4,017. When we come back here, we'll take a look at Pascal's triangle in order to solve the binomial theorem.